In general, the process for any random variable, when you're given the probability density function, okay, so to find the moment generating function, then you just take the expected value of e to the power t times x. Okay, so this is going to be, if it's discrete, here you can see it's discrete, it goes from 0, 1, 2, it's jumping. Okay, so this is discrete, I'm going to have the sum. Okay, we're not going to see the integral until we get into continuous data. Okay, but for now we've got the sum. So this is the sum of e to the power t times x times the probability distribution, which is given here. Okay, so I'll just sub that in. Okay, what I want to do generally, of course, is take out anything that has nothing to do with here the index. Okay, so 3 over 4 has nothing to do with the index. And really what I want to do is make something work so I can get rid of this infinite sum. Here they both have common powers of x, so I'll just put that together then. Get e to the power t divided by 4, all to the power x. This is, of course, a geometric series that I can use my identity for. I get 3 over 4 times 1 over 1 minus e to the t all over 4. Okay, so just simplifying this slightly, I get the moment generating function. I like this form just because it is nice for derivatives. Okay, so if I want to find the expected value and variance of x, I can just take the derivative of this moment generating function that I just found. Okay, so here I'm going to take the derivative with respect to t. What is the function? I said it's 3 times by 4 subtract exponential to the power t. Okay, and then here I've got all of this term being raised to the power -1. Okay, or being divided. Whatever way you want to type it in is fine if you want R to find the derivative for you. Here's the derivative. I'll go ahead and find the second derivative as well. Okay, so I'll find the second derivative. Okay, so there's the derivative and the second derivative. Here, what I'm going to do is I'm just going to sub in t is equal to 0. Oh, what's going on here? Power. Sorry, I guess that doesn't work out so well. Anyways, you get this is the derivative here. This is not a hard derivative to do. You probably shouldn't get too dependent on computers anyways, I guess. But if t is equal to 0, I sub in t is equal to 0, of course, this just becomes a -1. This becomes a 1. And what I get here is some cancellation. I get -3 divided by 3 to the power 2 times by -1, which will just be 3 divided by 3 squared, or 1/3. Okay, getting the second derivative then, let me just see if this will work for the second derivative. I'm not really sure why that didn't work for the first derivative. It also doesn't like that. Not sure why that was working earlier and now it isn't. However, second derivative will factor to this. I'll sub in t. I'll be able to simplify here. Here I'm getting this is just 1, this is just 1, this is just 1. And what I get when I simplify is the expected value of x squared is 5/9. Okay, when you're dealing with actual values instead of general distribution, sometimes you get some really nice values coming out of it. So the variance then, we've got the expected value is 1/3. The variance is the expected value of x squared, subtract the expected value of x all squared. This is 5/9, subtract 1 over 3 to the power 2. Okay, I get 5/9, subtract 1/9, and the variance would be 4/9. The standard deviation would be √4/9.